Ryan Ward from the University of Liverpool, and this work was done in collaboration with Shami Rahman from the University of Lincoln, Sophie Werger from the University of Liverpool, and Alan Marshall, also from the University of Liverpool. There are many problems that might arise whereby being able to cheaply, accurately, and easily be able to predict people's cross-modal correspondences would be greatly beneficial, even more so with novel odorants such as perfumes. One such problem is that when designing interactive and immersive experiences, designers are often presented with an incomplete set of sensory cues. So what are people expecting cross-modally? How do we conform to these expectations? And what are the desired effects? Designers often need to fine-tune interactive and immersive experience to suit a particular desired outcome. For example, if we take a restaurant scenario, it will be greatly beneficial to enhance the perceived pleasantness of the experience, consequently increasing the perceived value of the food and increasing the chance the customer will return. To determine what cross-modal associations people have towards an odour, extensive psychological tests are usually conducted, but this need not be the case. For a new perfume, it would stand to reason that the packaging should A. reflect the smell of the odour, and B. aim to maximise the perceived pleasantness and value of the product. Psychological tests are usually conducted to determine what cross-modal associations people have towards that specific odour, such as the colour, the shape of the packaging, and which musical genre best represents the odour. For example, people are in general agreement that the lemon odour is more angular in nature and vanilla odour is more rounded in nature. However, uncovering these cross-modal associations is a tedious, time-consuming, and a very costly process. To uncover these associations, to conform to the sensory expectations of the user, thereby enhancing how pleasant the experience is perceived and its perceived value, as well as improving task performance. It would also be beneficial to modulate how the odour itself is perceived. For example, it has already been shown that changing the colour of a wine glass can bias the opinion of an expert wine taster. Being able to predict cross-modal correspondences will save time, money, and will lead to better designs, as the need to conduct these extensive psychological tests will be eliminated. This work has two main research questions. The first one is, can we tune an electronic nose to the cross-modal perceptual axis? And the second is, can we build a computational model to predict human olfactory perception? In this study, we specifically focus on capturing and predicting the cross-modal correspondences between odours and colours. To do this, we collected the cross-modal odour-colour correspondences from 68 participants. 16.7 million possible colours could be selected from the CIELAB colour space. This colour space was chosen because it was perceptually uniform. Participants could select a colour by sliding through the L star channel. All A star and B star values for the currently selected lightness level that fit into the sRGB colour gamut were displayed to the participants. The lighting in this room was kept consistent by using a daylight setting on the overhead luminaire in a light-proof room. This negated the effects of different lighting conditions on how the participants perceived the colour. 10 marked unessential oils were used. These oils were covered in white tape to avoid any adverse associations between the colour and the oils and potential correspondences. Consistent colour profiles were generated in our prior work using the participants' colour selections. For example, the odour lemon has a consistently yellowy green color profile, and coffee has a reddy brown profile. An electronic nose was used to extract the physiochemical features from the olfactory stimuli. An electronic nose is an array of gas sensors coupled with a pattern recognition system. These sensors respond to odours in the vapour phase, which is more often than not indicated by a change in resistance. We first recorded 10 odours, 10 times each, for a total of 100 samples. Some pre-processing was performed on the eNote recordings to reduce the dimensionality of the data and to remove some of the sensor noise. The eNote recordings were used as input in the generated models. We then took the median color for each of the color dimensions separately. This revealed correlations of 0.56 for the L star dimension, 0.56 for the A star dimension, and 0.59 for the B star dimension. These correlations indicate that most of the variance for the color dimensions was captured when collapsing the ratings across participants. Learning algorithm for predicting people's color associations. 4 different algorithms were tested. These were linear regression, support vector machine, random forest, and Gaussian process regression. The latter gave the lowest error in all 3 of our color dimensions. Therefore, we decided to select the kernel function that best represented the underlying perceptual data. Process regression models were tested using a leave one odour out approach. All recordings for one odour were left aside for testing. The remaining recordings were used for training. This was repeated until all odours have been in an unseen state. Pearson correlations were then conducted on the predicted versus actual values. A correlation of 0.49 was obtained for the L star dimension, 0.44 for the A star dimension, and 0.42 for the B star dimension. To see how close the human-machine correlations were to the human-human correlations, we calculated the relative percentage between the two, revealing that L star was the closest with a percentage of 86.33%, followed by the A star dimension with a percentage of 78.66%, and the B star dimension had a percentage of 17.11%. The conclusions of this work are that an electronic nose can be tuned to the olfactory perceptual axis. In this case, we have demonstrated colour. It is also possible to predict the colours associated with the odours, and that the cross-modal odour-colour associations are partly encoded into the molecular properties of the olfactory stimuli, and therefore it is capturable by our machine, an electronic nose. It is important to stress the limitations of our findings, which is that only a portion of olfactory perception is hardwired, which our findings reflect. However, olfactory perception is also influenced by many other dimensions that are not the physiochemical features of the olfactory stimuli. This includes culture, context, learning, prior experience, and multisensory convergence. Future work could include determining the extent to which the cross-modal perception of odours can be predicted, e.g. the perceived smoothness of texture, musical genres, and the perceived angularity of the odours. The findings reported here could also be improved upon by including a larger sample size of odours and the colours people associate with them, as well as investigating if people's cross-modal odour-colour correspondences can still be predicted using novel odours, such as odour mixtures. The potential of predicting human perception is not limited to odours. It may also be possible to predict the cross-modal correspondences attributed to taste. This could be done using an array of chemical sensors coupled to a pattern recognition system, otherwise known as an e-tongue. A cyber-physical system could be developed whereby the cross-modal properties of odorous objects can be changed to determine the effects they have on inducing bias. For example, if two different physical configurations for displaying odors are present, can we generate the same percept by changing the cross-modal properties, such as changing the lightness of color assigned to the odorous object?